Hello, good evening everyone. My name is Akhil and we are conducting this weekly live sample problem solving sessions for the basics of material engineering course every Tuesday from 7 to 8 p.m. So let's begin the today's session. Yeah. So this week was mainly about cyclic loading of the systems, not static loading. So we'll have fatigue kind of failures. So the first question is related to that. So here we are given four options. Not four options, four different cases where sigma max and sigma minimum were given. So our job is to find the stress range, alternate stress component or the amplitude, mean stress component, stress ratio and amplitude ratio. Okay. Yeah. So for case A, first let's see the formulas for the stress range. So stress range is basically the difference between the maximum minus minimum. So it is the total. So let's say you have some kind of cyclic loading. Now in this case, this is the maximum and this is the minimum. So this is the stress range. Okay. Now what is the alternate stress component? Sigma A. So this is basically the amplitude of the cyclic loading. So in this case, first we need to, let's say, assume this as the mean, then this would be the amplitude. Okay. So this is sigma m, and sigma amplitude in this case would be the range by 2. So sigma max minus sigma min by 2, and the mean would be the average. Same, yes. So it basically means like about some mean value, your stress is changing. That's it. So that is why it's called alternating stress component, or in our case we can just say amplitude. Both are same. Okay. Yeah. Now stress ratio. So stress ratio is defined as the minimum stress by maximum stress. Okay. And the amplitude ratio. So that is defined as the amplitude stress or alternating stress component by the mean stress. That's it. Okay. So this is how these are defined. Now, yeah. So let's calculate these for different options, different cases we have. So stress range for this would be directly maximum minus minimum. So 500. For this, the stress range, stress is going from 500 to minus 500. So the range would be 1000, right? Now in this case, 1000 to minus 500, so 1500, and 1000 to 500, so range would be only 500. Now if you see here, maximum is 500, minimum is 0. So that means it's actually going from, uh, yeah, yeah. So it is like this, right? So this is not a fully reversible load. There are certain names for each of these. 1 second. Yeah. So this is a repeated load. If one of the mean or maximum is 0 and the entire stress is only on one side. If this is 0, then one of them is 0, then it is called a repeated load. So this is a repeated load, repeated type of load. Okay. So even 0 and minus 500. This would also be a repeated load. Okay. Yeah. Now the second one we have 500 to minus 500. So this would have mean as 0. So that is a fully reversible cycle. So fully reversible cycle. Okay. Yeah. So these would be fluctuating loads. They won't come under. This is not a repeated and this is not fully reversed. So these are the other types. Okay. So now let's calculate the amplitude. So for the, no. Here, as far as I know, the alternating stress component means only the amplitude. That's it. There is no. I haven't come across alternating load type. Okay. Yeah. So the amplitude would be maximum minus minimum by 2. So here 250. So here 500. 700 is basically range by 2. So here it would be 750 and here it would be 250. Okay. Now what is the mean? So mean of sigma max and sigma min here 250. So 500 minus 500, this is 0. So here if you see in fully reversed load the mean would be 0. So that is how you can easily identify a fully reversed load. Okay. So now 1000 and minus 500. So the mean would be 250 and 1500. So the mean would be 750. Okay. Now let's calculate the stress ratio R. So sigma min by sigma max. So this would be 0. Okay. And this would be fully reversed load, minimum minus maximum would be minus 1. So these two are the characteristics for a fully reversed load. Mean would be 0 and R would be minus 1. Now this would be minimum minus maximum minus 500 by 1000, so minus 0.5. This is 500 by 1000, so 0.5. Okay. Now amplitude ratio. So sigma A by sigma M. So here it is 1. So this is infinite, right? And 50. This would be 750 by 253 and 250 by 750. So 1 by 3. Okay. So this is how you can estimate all the components for a given stress system if you are given sigma max and sigma min. So in the same way you can actually interrelate these also. Like let's say you are given R and A or sigma A and sigma M. How will you get sigma max and sigma min? All those you can get from these relations. Okay. So hopefully this is clear. We'll move on to the next question. Yeah. So now here you are given amplitude ratio. No. You are asked amplitude ratio in terms of stress ratio R. Okay. So what exactly is stress ratio? Sigma min by sigma max, right? And what is amplitude ratio? Sigma A by sigma M. Okay. Now we need to estimate amplitude ratio in terms of stress ratio. So how can we, what is amplitude actually? Sigma max minus sigma min by 2 and mean sigma max plus sigma min by 2. Okay. So this will make it sigma max minus sigma min by sigma max plus sigma min, right? Now, okay, I think there is a lag. Okay, let me disconnect and connect the screen right now. Yeah. So here we have just written. Okay, this is gone again. Is it visible now? Yes. I just write amplitude and sigma mean in terms of maximum and minimum, like we have seen in the earlier problem. Okay. Now in the numerator and denominator, let's divide it by sigma max. So then this would become 1 minus sigma min by sigma max, and this would become 1 plus sigma min by sigma max. Okay. So what is sigma min by sigma max? R, right? So is this clear? So how can we estimate A and R, interchange A and R? Okay. Uh, So that numerator I have taken sigma max common, and denominator also I have taken sigma max common. So what I am doing is sigma max if you take common, so this would be 1 minus sigma min by sigma max, right? So here also if I do in denominator also, okay, now this gets cancelled and this is what you will be left with, 1 minus sigma min by sigma max by 1 plus sigma min by sigma max. Yeah, and sigma min by sigma max is r, so 1 minus r by 1 plus r. Okay, so now you can, if similarly you can interchange from r to a also. So for that you can just simply add a plus 1 on both sides. Okay, so I am adding plus 1 to both LHS and RHS. So 1 minus r plus 1 plus r by 1 plus r. So what would this be? So r gets cancelled, 2 by 1 plus r. Okay, now a equal to 2 by, okay, we want r in terms of a, right? So let's interchange this. So 1 plus r is equal to 2 by a plus 1. Okay, so 1 plus r I am bringing it to the left hand side, a plus 1 to the right hand side. Now r is equal to 2 by a plus 1 minus 1, and then r is equal to 2 minus a minus 1 a plus 1. So this is 1 minus a by 1 plus 1. Okay, so this way you can interchange. If you know a, you can calculate r, and if you know r, you can calculate a. Okay, yeah. So I hope this is clear. Let's move on to the next question. Yes. So what are the 4 stages in crack this thing, fracture? So first the crack initiation, crack propagation, and then next failure, right? So which will take the most time? The usual time duration for crack initiation stage is much higher than that of crack propagation stage. So is this true or false? Which will take more time, initiation or the propagation? Yes. So this is false, and the time taken by crack propagation is actually the longest in the process. Okay. Yeah. Yes, I think so. I think so. So just initiation, and then when it starts, you are saying basically single crack can become two cracks, right? So yeah, I think that is part of propagation. So after that, it will fracture completely. So okay, now one question we have. So a machine component is made up of high strength steel, and that shows endurance limit. So here it's clearly mentioned that it shows endurance limit. So do you know any materials which don't show endurance limit? Yes, exactly. So only steels and irons show this endurance limit. Aluminum and copper doesn't show. So for them, there is a different way to, we won't say endurance strength, it's called something else for them. And only steel will have endurance strength, and the endurance strength and ultimate tensile strength are related. So here we were given the endurance strength at 10 power 6 cycles, and we are asked ultimate tensile strength and yield strength. So do you know the relation between endurance strength and ultimate tensile strength without any correction factors? 0.5, 0.4 is for iron. So for steel, sigma endurance is equal to 0.5 into ultimate tensile strength. Okay. Yeah. For iron it is 0.4, but for steel it is 0.5. Okay. For iron, so this also there is some condition. This is true till sigma UTS is less than or equal to 1400 MPa. Okay. If it is more than 1400 MPa, then you should take directly Okay, this is for irons. So here we were given 360 MPa as endurance strength. So sigma UTS is 720. Okay, so this 720 is less than 1400. So this is valid. Okay, yeah. And for iron, sigma endurance is 0.4 sigma UTS till 400 MPa. So these equations are there in your textbook, so you can just check it out. Okay, yeah. Now, do you know, can we estimate yield strength from this? No. Like yield strength never comes into picture when we are talking about endurance strength and ultimate tensile strength. Okay, yeah. So yield strength can't be calculated from this. We need some more data. Okay. So yeah, that is for this question. Yes. So which of the following can be considered for fatigue strength correction factors? So basically, what will affect the fatigue strength? What are all the factors which can affect the fatigue strength? So variability in specimen fabrication and surface preparation. So do you think that should affect? Yes. So if the surface is very smooth or surface is little rough, based on the type of finish, actually the fatigue strength will change, and the fabrication techniques could also affect. So will affect. And what about the types of applied loads? You have bending load and you have axial loads, torsional loads. Will that play a role in determining the fatigue strength? Yes. Why do you think so? Yeah. So the reason is in bending load, you know that if you are looking at the axial stress developed due to bending torque, bending moment. Okay, let's take something like this, and you are bending it. So because of the bend, it has taken this shape. So here you see at this surface, it is in tensile, right? Here it is in compression. So here the load is changing across the surface, across the cross section. But if you are taking an axial load, here load will be same across the cross section. Okay. So that is why both are not same. That is why the type of applied load will have a role. Okay. So what about dimensions and geometry? Yes. Because if you take the simple bending case, in that case, if you the bending stress is proportional to the distance from the neutral axis, right? My by I, sigma bending. M being the bending moment. So dimensions will also have an effect on the fatigue strength. Okay. Yeah. So what about yield strength of material? Yeah, it doesn't come into picture. Yes. So all these factors can affect the fatigue strength. So each of these will have a correction factor. So we will see that later on. Based on that, how can you do the SN graphs? And okay. Prabhanjan, were you able to follow? Are you able to follow the Prabhanjan? Okay, let's move on to the next question. Yes, thank you, Prabhan. If you have any doubt, you can either unmute yourself and ask, or you can ask in the chat also. I will be happy to explain. Yes. So let's go to the next question. Yeah. So now stress and life data of steel specimen is described by this equation. So we are already given an equation which relates the stress and life. Okay. Now if a component is subjected to 300 MPa alternating load and service life of 3000 cycles. Now what are the factors of safety in stress and in life? Okay. So do you have any idea on how to go from here? So does anyone know what is factor of safety in life and how is it different from factor of safety in stress? No, 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 no. Yeah, you will see now. I will explain. So one thing is factor of safety in stress. How do you estimate is you estimate the fatigue strength corresponding to the service life. Okay. So let's see here. Now we want it to be run for 3000 cycles, right? So the corresponding fatigue strength for 3000 cycles would be 1000 into n, 3000 power minus zero point 0.1. So this would give, yeah, almost 4 449.04 MPE. Okay. Now this is the fatigue strength at 3000 cycles. So if you draw this graph, this would come something of this sort with n. This is in log scale and this is s. Okay. Now when you are applying using it for 3000 cycles, so this is the maximum stress that you can apply, maximum alternating stress that you can apply. Okay, till failure. So that stress is actually 449.04 MPa till 3000 cycles. Now the factor of safety in stress. So what I mean is now when you are using it for 3000 cycles, unless you go to this load of 449 MPa, it won't fail. So if you are below that, you are safe. So the factor of safety is 449.04 by 300. So this is almost 450. So it's 1.5. Okay. So this is the factor of safety in stress. Now when you are asked factor of safety in life and you are given alternating stress of 300 MPa. Okay. Yes. 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 It's the alternating stress component or the stress amplitude. So this SN graph is these equations are actually for an amplitude versus cycle. So mean is not in the picture here. Okay. So and this is they will specify actually when they give this equation. This is for some corresponding sigma m. So when nothing is given, you assume that sigma m to be 0. Okay. If it's yes, yes, this is the fatigue strength, fatigue factor of safety, right? So only the alternating stress, the stress which actually changes, keeps changing. Yes. So this is fatigue factor of safety. So that means the loads are changing. When you have a constant load, then you don't do this. Okay. This is not how it works. This is only for so when it is a non-changing course, then that would be n equal to 1 case, right? It's a so then you do with yes, you put n equal to 1. So Murtala, can you mute yourself, Murtala? So if you put n equal to 1, then you will get s. So that s you can take for the amplitude, but here this mean is taken as 0. Okay. So let's say if this is the graph, this is sigma m equal to 0, some value. So this is how it increases with sigma m increasing. Okay, and this is the fatigue strength of factor of safety. Now if you have this mean stress also, then you need to use extra things which will come in next week. Murtala, can you mute? Okay. Uh, is that clear, Suresh Babu? Yeah, with the sigma m also being there, we will see that next week actually. Those will come. So yeah, now if you want factor of safety in life, so for this applied stress you will see the maximum number of cycles it can handle. So now you know the strength already, the stress which you are applying, you need to find the n corresponding to that 300. Okay, now this would give n power minus 0.1 is equal to 300 by 1000, so 0.3, so n is, okay. So is this clear? Now let me just check this value, 0.3 power 1 by minus 1 by 0. So this is almost 1.69 into 10 power 5 cycles. So what this means is, if your alternating load is only 300 MPa, then it can sustain 1.69 into 10 power 5 cycles. So that means if this N we are looking at 3000, right? So this is actually almost 100 into 1000. So this would be somewhere here. Let's take. So now factor of safety in life. So at this stress level, it can handle this many number of cycles, but you are only using it for 3000 cycles. So the factor of safety would be the ratio of these two. Okay. So this is almost 56.4. So this is the factor of safety in life, and this is the factor of safety in stress. So actually the final effective factor of safety would be this only, 1.5, because that is the lower value. But you might be asked both. And in these situations, you would actually be specified what they are asking, factor of safety in stress or factor of safety in life. Is that clear, Suresh? And everyone? Yeah. Okay. So now let's move on to next question. Yes. So it's given a non-ferrous alloy subjected to loads case A, B, C. Here we are given maximum and minimum. Rank them as per their life till fatigue failure. Yes. So now can anyone try to guess how should we proceed with this first? We have A, B, C. Then we were given maximum and minimum. 500 minus 300, 600 minus 400, 400 minus 400. Now first thing in these situations is you need to estimate the sigma amplitude and sigma mean. Okay. So what would be the amplitude? 400, because 500 minus of minus 300, 800 by 2. Okay. So 600 plus 400 by 2, so 500, and here amplitude would be 400, right? Next mean. So 500 minus 300 by 2, 200 by 2, so this would be 100, so 100, and this would have 0. So is this clear? Now in general, if you have an SN curve, so the reason why here it's specifically mentioned it's non-ferrous alloys are because ferrous alloys we know that they show this endurance limit. So that means they will have something like this. So they are clearly mentioning that this is a samples which are not ferrous. So they don't show this endurance limit and they will have something like this. Okay. It will be a continuous with respect to the number of cycles. Okay. Now, so here we actually have sigma A is the y-axis and n is the number of cycles. Now we have to rank them as per their life. So which can sustain more number of cycles? In that order we have to rank. So with increasing mean stress, so the number of actually I have given here wrong. So with the mean stress increasing, actually it will fail much earlier. Okay. So with sigma m increasing, the graphs will be down. So that means here if you take two cases, amplitude as mean as 0 for this and mean as 100. Okay. So if mean is 0, that means for a given amplitude, it will sustain more number of cycles. Okay. Now let's take amplitude as 400 and 500. These are the two cases we have. So let's take this as the 500 case and this is the 400 case. Okay. And this is mean equal to 0 and mean equal to 100. Okay. Now this would be, these are hypothetical curves in general for non-ferrous materials. Okay. So this is how they qualitatively look. We don't know the exact distribution, but qualitatively this is how they look. Now, yeah. So A is amplitude being 400 and mean is 100. So that would be mean is 100, amplitude is 400. So this would be the number of cycles that sample A can withstand. Now B is 500, 100. Okay. Now C is 400 and 0. So this is point C, this is point A, and this is point B. So is this clear? Now which can withstand the maximum number of cycles? So C can withstand maximum number of cycles greater than A and greater than B. So is this clear to everyone? So if you are given maximum minimum or anything, first you need to estimate the amplitude and the means. And from there you can draw a qualitative graphs, and from that you can estimate the or rank them based on the number of cycles they can withstand. Okay. So I think you have a similar question in your assignment also, so it should be helpful. Yes. Now next question. So we have to draw the SN plot for a steel bar. So steel bar, so it shows endurance limit. So it shows that saturation kind of curve after 10 power 6 cycles. So equations for HCF resin. So HCF means we are only looking at 1000 to more, 1000 cycles to more. So that is HCF, high cycle fatigue. Okay. And estimate life if amplitude is 600 and amplitude is 900. Okay. And we were only given SUT, nothing else. So only SUT is equal to 1500 MPa was given, and steel and HCF resin. So these are the only data we are given, and we are supposed to draw the SN plot and give the equations also. Okay. So to actually draw the SN plot, so this is 1, this is 10 power 3, 10 power 6, 10 power 0, 10 power 1. Okay. So since we are mentioned steel, it has endurance strength. So since ultimate tensile strength is 1500 MPa, what should be the endurance strength? Anyone? No, I am talking about endurance strength. Yes, 0.5 to 1500. But we have a special case here. If it is more than 1400, then it should be, yes. So because SUT is greater than 1400 MPa, endurance strength should only be 700 MPa. Okay. So endurance strength is actually Strength. Okay, okay. Yeah, okay. So then, okay, let's call it endurance limit. Okay. So 700 MPa. Okay. So this is one point at 10 power 6 cycles. If it's not mentioned, then usually this endurance limit is taken at 10 power 6 cycles. Okay. So this point, one point in the graph is 700 comma 10 power 6. Okay. Now at 10 power 3 cycles. So the region, the interaction between low cycle fatigue and high cycle fatigue. In between this, now to get this point, now yeah, as you were saying before, SM, this is 0.9 SUT. Okay. So 0.9 into 1500. So this is 1350. Okay. So this point is 1350 comma 10 power 3. So this is the graph in the HCF regime. Okay. Now if you want in the LCF regime also, so usually that would start from 1500 to this point 9. Okay. So this is SUT itself. Okay. Yes. Now in between these two graphs, now we have drawn the graph. Now we also have to give the equations in the HCF regime. So that means we need to give the equation for this part. So we know that any this SN life cycle follows this kind of equation, and we know we need to find these two constants, and we have 2 points. Okay. So one point is 1350 comma 10 power 3 and 700 comma 10 power 6. Okay. So now let's substitute these two. Let's do log here. So log 10 of S is equal to log 10 of A plus B log 10 of A. Okay. Now let's substitute the first point. So log 10 of 1350 is equal to log 10 of A plus B into log 10 of 10 power 3. And then second one, if you substitute, log 10 of 700 is equal to log 10 of A plus B into log 10 of 10 power 6. Okay, this is equation 1, this is equation 2. Now if you subtract equation 1 from equation 2, okay, so that means log 10 of 700 minus log 10 of 1350 is equal to, see, because log 10 of A, log 10 of A, so it's 0, and then B log 10 of 10 power 6 minus B into log 10 of 10 power 3. So is this clear till here? Okay. Now there is a log 10, log minus log, so this you can write as this way. Inside log you can divide them. Now this is log 10 of 10 power 6, so this is 6b minus log 10 of 10 power 3, so this is 3. Okay. So now you can actually estimate b as 1 by 3 of log 10 of 700 by 1350. Okay. So this would actually give you b as minus 0.095. Okay. Now once you know b, you substitute back in equation 1. So log 10 of 1350 is equal to log 10 or directly in the main equation. So S is equal to A into n power b. We know 1350 is equal to A into n is 10 power 3 b minus 0.095. So this way you can estimate A. So if you substitute here, you would get A as, let me calculate it quickly. So 1350 by 10 power 3 power minus 0.095. Okay, so 2604 cycles, almost 2604 MP. Okay, so the equation is 2604 into n power b. Okay, is this clear now? So by just knowing ultimate tensile strength and the material type, we can actually estimate the fatigue, we can actually draw the fatigue graph on our own and give the equation also. Okay, now if SUT is less than 1400 MPa, so here you will directly take half of SUT. Okay, here it will directly come half of SUT if it is less than 1400 MPa. Here it's because greater than 1400 MPa, you fix it to 700 MPa only. Okay, yeah, so yeah, is this what you want? Yeah, 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 because everything else is there, we are just getting A now. Everything else is no. Okay, yeah. Now we are asked amplitude stress, alternating stress 600 MPa and 900 MPa. We are supposed to estimate the life. Okay. Now, so can anyone tell me for this what we should do now? Now we have this graph 1350 at the SM and 700 at the endurance limit. Now alternating or amplitude is 600 MPa. Mean is taken 0. If it's not given, so mean is 0. So this graph is valid. Now in that case, amplitude is given as 600 MPa. One case. So what would be the number of cycles that it can withstand? Anyone? So now can anyone tell how many cycles it can withstand? No, it's the endurance limit. It's less than the endurance limit. So it can withstand as many cycles as you want. It will never fail. So this is the stress for infinite life. So sigma A is equal to 600 MPa is actually less than SA. So infinite life. Okay. Yeah. So in the second one, we are asked sigma A is 900 MPa. So what would be the life? Oh, okay, it's visible. Yeah, yeah, but because this graph is not to the scale, you can just because we know the equation, you can directly put in the equation. 900 is equal to 2604 into n power minus 0.095. So 900 by 2604. Okay. So if you calculate this, you will get the number of cycles corresponding. So let me just do it quickly. 900 by 2604 power 1 by minus 0.095. Okay, 7.1 into 10 power 4 cycles. Okay, so this point would be 900, so around 7.1 into 10 power 4, right? Yeah. So it's close to 10 power 5. So this is 900. Okay. Yeah. So this is how once without yeah. So this is how without actually knowing anything. If you know that it is steel, and if you know the ultimate tensile strength of that steel, we can actually do a guess estimate for the factor of safety in for a given amplitude. Okay. So this is because researchers have already done all this data, and this is how you can do this zero point 0.9 SUT, this zero point 0.5 SUT, all these equations were developed after years of research. Okay. So if you follow SAR's lecture, he would have talked about one researcher who had spent 20 years determining this kind of graphs for different types of steel. Okay, because of all their work, now if you just know the ultimate tensile strength and the material, we can easily estimate the factor of safety in life or estimate the number of cycles it can withstand. Okay. So now let's move on to the next question. Yes. So we have seen earlier question that the type of load, type of the size, and other things, specimen, how it's made, surface finish, all these factors will affect this endurance. So let's see how do they affect, and if they are affecting, what would be the corrected fatigue endurance limit. Okay. So here we are given SUT is equal to 1000 MPa. So what would be the uncorrected fatigue endurance limit? And it's given steel. So what should be the endurance limit? Yes. Okay. So it is 500 MPa. Okay. Yeah. Now shape is given as round. Okay. And size is given as 100 mm. So what is the correction factor if the size is 100 mm? So all this will actually be in your textbook. So you need to actually know that exact equation, or in the exams you would actually be given what is that relation or some charts. So uh, let's see this. So for dia less than 8 mm, C size, the size based correction factor is 1. So when the dia is 8 mm to 250 mm, in that C size is 1.189 into d power minus 0.097. Okay, but this size is a function of the type of load. Okay, and if it is an axial loading, whatever the dia, so you need to be like carefully look at what type of loading also when you are calculating the size related correction factor. Okay, so for axial loading, C size is always 1. Okay, independent of the size. So this equation is not valid actually. Okay, so this equation is not valid when it is an axial loading. In other case it is valid. So here C size is 1. Okay. Now surface, due to surface finish, what should be the, so for that if you see the textbook or SAR slides, and this is ground surface finish. So for ground surface finish, uh, A into SUT power B with, for ground A is 1.58 and B is minus 0.085. Okay. So what should be the surface based surface finish? See, ground based surface finish correction factor. SUT is given as 1000 MPa. So minus 0.085. Okay. So let me calculate this. 1.58 into 1000 power minus 0.085. So C sub is 0.8783. Okay. Now we got the two correction factors due to size and surface finish. Now its loading is given as axial. So what should be the loading correction factor? So for axial loading, loading correction factor is 0.7. Okay. And for bending kind of loading, it is 1. And if you have a torsional kind of loading, you need to actually estimate the maximum stress or the von Mises stress for that torsional stress, and then use correspondingly. Okay, 1 only mostly. So just check the SAR slides in that or the text. So in this case, because it's axial loading, the loading is directly taken as 0.7. Okay. Now, what are the other things? We have done the size, surface finish, loading. Temperature is 500 degrees Celsius. So C temp, there is a equation given directly. So 1 minus 0.0058 into T minus 450 only if temperature is greater than 450 degrees Celsius and up to, okay, okay, so only in this range this is valid. So if T less than 450 degrees Celsius, then C temp is 1 only. So there is no need to take temperature correction factor. But here temperature is given as 500 degrees Celsius. So C temp is equal to 1 minus 0.0058 into T is 500 minus 450. So 1 minus 0.0058 into 50. Okay. So let me calculate that. 1 minus 0.0058 into 50. 0.7. Okay. Yeah. So now we are done with this temperature also. Now reliability correction factor. So we are given 99.99, 99.9%. 99.9. Okay. So the reliability has 99.9 percentage only. Yeah. So what does that mean? Can anyone tell me? Yes. For every 1000 specimens, only one should fail. Okay. So that is this. And for this, there's actually a table corresponding to what is this reliability percentage and the C reliability. So for 99.9, this is actually is 0.753. Okay. So this is also in your slides and the textbook, this data. So these equations are also from the textbook only. I'm not just making them up. So if you just check your textbook, or they are mentioned in the slides also. Yeah. So now we have the correction factors for everything. So let's see the corrected endurance strength directly. So corrected endurance strength is all the factors. First factor size, surface, loading, temperature, and we have reliability into the uncorrected one. Okay. Let's take this as uncorrected. So S is equal to, what is the size? So we got 1 because it's axial loading. Okay. And surf 0.8783. type loading 0.7, temperature 0.71, and reliability 0.753 into uncorrected endurance limit is 0.5 SUT, and SUT is less than 1400, so it's just 0.5 SUT, 500 MPa. Right? So the corrected endurance strength. So if you do all these calculations, multiplications, then let's see what we will get. So 0.8783 into 0.7 into 0.71 into 0.753 into 500. So 164.35 MPa. So you see, previously without all these correction fractions, it's actually 500 MPa. Now because of all these correction factors, the endurance limit has dropped down to just 164 MPa. Okay. And we are also asked to create equations for SN line and draw them also. So I want to do that exact thing, but I will give you the initial these things. So because this is given as iron ferrous based, so this endurance will happen at 10 power 6 cycles, right? And how at 10 power 3 cycles, what should be the SM? Is directly 0.9 SUT. But if it is an axial loading, actually, let me see. Yeah. So SM also, this is for bending kind of load, and 0.75 SUT for axial load. Okay. So you need to see that also. So let me just check this once. Size factor, yeah. Yes, SM is 0.75 SUT for axial loading. So now we know 0.1. Let's take this as 10 power 3 and this as 10 power 6. So this point is SM comma 10 power 3. So which is equal to 0.75 into SUT. So 0.75 into 1000, so 750 MPa. So 750 comma 10 power 3 is this point, and then endurance, corrected endurance is 164. So that would be this point. This point is SU comma 10 power 6 is 164.35 comma 10 power 6. Okay. Okay. So this is the corrected graph. So if you didn't correct it without any correction factors, okay. So if you didn't use any correction factors, so this is what you would get. Okay. So basically, let's say you are loading it to 200 MPa. So if you are using the uncorrected fatigue endurance strength, it will tell you that it will never fail. But if you correct it, then it will actually fail at this number of cycles. Okay. So that is why we need to do all that corrections. If you use the uncorrected one, you'll actually fail before and then it will be a major issue. It will actually fail. It won't be designed correctly. So because now you know these 2 points, you can actually estimate the equation S is equal to A into N power B, like we got in the earlier question. Okay. Is this clear? So is this clear, everyone? Suresh and Ajay? Okay. So in SARS in the NPTEL also you would actually find some questions extra document where they have done similar problems. So you can get some more information from there also. Okay. No, I just like if amplitude of 200 is applied, what will be the life? Yeah. Yeah. So so that is it for today. Thank you everyone. I will upload these documents and the video mostly tonight. Question 4. Okay. Yeah. Yeah. This is question number 4. Yeah. Okay. Yeah. So thank you. I'll upload these documents. This document I'll upload in like half an hour only in that Google Drive folders, and the video mostly tonight. So thank you everyone. You can log out. Thank you.